Today I'm going to be doing a quick review of powers of 10. So if you'll remember in the place value system based on 10, I have individuals in the units or sometimes called the ones place. And when I get all the way up to 9, I can't fit any more in that place value. So when I have a whole group of 10, I move over to the next place value, tens. Then I can count in the tens place, but again, once I get to 9, there's no more room. I will then move over to a group of 10 tens, and that is going to be 100. So 10 tens all stuck together is going to give me 100. Now, I can fill up this place value with 9 of these, but then once I get to 10, I got to move over again. 10 times 10 times 10, when I have it multiplied 3 times out, is going to give me 1,000. So you can see here that I have 10 times 10, that gave me my 100 square, but then I stacked it. And 10 more stacks all the way up is going to give me 1,000. Now, you can do this with any number. I could have base 2. I could have base 60. I could have all kinds of different bases. When you use base 10, some really fun things happen in the patterns of the zeros. And so that is one of the reasons why a lot of the numbers that we use today are in a base 10 system, because they are so very easy for us to be able to use our little human brains for. So I got 10 digits on my hands, and that makes 10 a very nice number for me to deal with. So let's just kind of show a written version of what I was just doing with the parts here. If I have 10 times 0, I don't have anything, it's just 0. If I have 10 times 1, I have 10 to the first power. I got one of them, it's just 10. If I take 10 times 10, I get 100. Boop. You'll notice 2 zeros here. 10 to the second power, my little exponent there. Because I have 10 times 10, there's 2 of these being multiplied together, and I get 100. Now, what if I take 10 times 10 times 10? Oh, well, we know what happens. I get 1,000, a cube. I have 3, so my exponent is 3. 10 to the third power just means 10 times 10 times 10. There's 3 of them. Now, if I took 10 of these, I would get 10 times 10 times 10 times 10. Oh, 10 to the fourth power. And I would get a big, long lineup, and I would end up with 10,000. So 10 to the fourth power is going to equal 10,000. And look, 1, 2, 3, 4, 4 zeros. But what if I take 10 times 10 times 10 times 10 times 10, and I get 5 of them? Okay, well, you're going to have 1, 2, 3, 4, 5 zeros. Count them back, put my comma. Ooh, 100,000. Well, what if I multiply that times 10? And I get 10 times 10 times 10 times 10 times 10 times 10. 10 to the sixth power is going to have 6 zeros. Start over here, count 3, 1,000,000. 10 to the sixth power is a nice, fun, short way of writing 1,000,000. Now, why would I want to be able to write this number in this format? Because if you are dealing with numbers that are very, very big or very, very small, this is a much easier way to write them out and to think about them in ways that make sense to our human brain. So for example, if I am an astrophysicist and I am looking at how the universe works and numbers and measurements that are absolutely huge, I don't want to write out all of those zeros. I'm just going to use an exponent instead. On the other hand, if I am a biologist and I am working with tiny, tiny cells and all of the parts of the cells that are even smaller, or maybe I'm getting into nanotechnology, I mean, that is tiny. I don't want to have to write out a decimal point and then 0, 0, 0, 0. I just want to be able to use exponents. And this is why the powers of 10 can be so very valuable. Almost all of the multiplication, division strategies, all of that work that we are learning with numbers and operation is all based on this powers of 10 work. So if you understand how this pattern works, you're going to be great pretty much on any kind of math that you're going to learn anytime soon. So let's talk about how I can use that. For example, the students in Mary's school collected 3,000 pennies over the year. What is this number written as a whole number multiplied by a power of 10? So I want to write the number 3,000 as a power of 10. Well, I'm going to break this down into some of its factors. I see the digit 3, so I've got the digit 3 times 1,000. 3 times 1,000 is going to equal 3,000. And I think we can all agree on that. If I have 3,000, it means I have 3 thousands. So 3,000s can all be written out as 3,000. Now, what if I break these apart? Oh, I make each thousand by doing 10 times 10, right? So if I break this apart, I can see that I have 10 times 10 times 10. So 3 times 10 times 10 times 10. So that's 10 times 10 times 10, and then I got 3 of them. Oh, this is pretty cool. Look how I made this one number into 4 numbers. Just fascinating. Amazing. So I can write this part here as 10 to the third. This digit is just going to stay the same. 3 times 10 to the third equals, oh yeah, 3,000. So I can write that simply as 3 times 10 to the third power. Now let's say I have Owen, who is using 3,000 craft sticks to build a model bridge. He has been asked to make 6 bridges for the local craft store. How many craft sticks will Owen need to make the 6 models? So he uses 3,000 craft sticks to build a model. He's been asked to build 6. And now we want to know how many craft sticks will he need. So let's write down the basic information, right? We've got that 3 times 1,000 because we already figured that out just a moment ago. But now we want to multiply this whole thing times 6. How many will he need for 6 bridges? Well, I can figure out 6 times 3 times 1,000. I don't actually want to count to 3 1,000 times or count to 6 3,000 times. I'm going to use powers of 10 to break these numbers down so that I can do this much faster. I'm going to use the patterns in the numbers. So 6 times 3 is 18. 18 times 1,000 equals 18,000. So when I write a number out, for example, when I write a number like this, I'm relying on my knowledge of place value in order for this to work. So powers of 10 and place value are why all of these algorithms work for us. All right, If I were using a base 2 or a base 5 or whatever, that algorithm doesn't work for them. Only because of base 10. All right, what we are going to do just for a moment is to just do a little bit of practice. So if I have, for example, this number right here, what would this be broken down into 10 to an exponent? So I can count 1, 2, 3, 4, 5, 6, 7 zeros. That is going to be equal to or the same as 10 to the 7th power. Very nice. Oh, I think I'm starting to get this. If I have 10 to the 2nd power, how would I write that? Oh, it means 2 of them. 10 times 10. Oh, 2 of them. It also means 2 zeros. Oh, 100. It's just simply 10 times 10. So the more you practice with this, the more comfortable you will get with it. And eventually you can start using that for rewriting numbers in the powers of 10 scientific notation. Now, in order for us to really get good at that, we're going to have to do a lot more practicing. So this video is just a very quick review of the concept. Here we are going to do just a little bit of the multiplication patterns with decimals. So if I start with the number 85 hundredths and I multiply this times 10, it's going to get 10 times bigger. That means I'm moving my decimal point over 1 space. So 85 hundredths times 10, I now have 8.5 or 8 and 5 tenths. If I take the same number and I multiply it times 10 to the 2nd power, I'm going to move it 2 spaces. 1, 2. Oh, that's just the number 85. It's a whole number now. Yay me. If I'm going to take 85 hundredths times 10 to the 3rd power, 1, 2. Oh, I ran out of things. Oh, right. There are hidden zeros in front and behind every single number to infinity and beyond. There needs to be one more little zero there. Now I have the number 850. What if I have 85 hundredths times 10 to the 4th power? Oh, I'm going to move it 4 places. 1, 2. Oh, I got to add 2 zeros. 2, 3. All right, 3, 4. I now have 8, 5, 0, 0. Find where my decimal is, count over 3, put in my comma. You should see a pattern of how the number is going to change by 1 place value for each power of 10. Now I can also go the other direction. If I know what the number times the power of 10 is, then I can also work backwards and figure out what the number was originally. So let's say that I have a number 4.2 times 10 to some kind of power. I don't know what the power is, and it equals 420. Well, this is where I started, this is where I ended, and I'm going to figure out how many place values I shifted over. So I'm going to figure out if I have to get my decimal point to here, so start here, end here. All right, that's 1, 2. Oh, it moved 2 place values, or 10 to the 2nd power. 4 and 2 tenths times 10 to the 2nd power, going to be 420. We're going to do another one of those. let's say I have 3 and 75 hundredths, and I've multiplied that times 10 to some unknown exponent. I don't know what it is. And I have the number 375. I know here's where it started. I know here's where it ended. So let's figure out the difference. So if my decimal point starts here and ends there, oh, 1, 2, hey! It's just the 2 again. We'll check that out. Let's do one more. So 5 and 67 hundredths times 10 to some power, I don't know yet, 5, 6, 7, 0, 0. Oh, sorry, I ran out of room there. I know this is where it started, and I know this is where it ended. So I go 1, 2, 3, 4. Oh, 10 to the 4th power. Oh, very nice, very nice. All right, so that is just one set of examples, and the more you work with this, the more comfortable you will become with it. So enjoy working with powers of 10.